Welcome to this session of the notes on the flyback converter. So we've been looking at the analysis of the flyback converter when the switch is open and also when the switch is closed. So we looked first at the scenario when the switch is closed, and we look at the scenario when the switch is open, and we did analysis. So we were on the analysis when the switch was closed. We looked at the final relationship between the input and the output voltage of the flyback converter, which was very similar to the back boost, and we talked about that. We started looking at the diode currents and the switch current. So what is the current which is flowing through the diode when the switch is open, and what is the current which is flowing? This is a typo over here, and this should be capacitor. So the diode and the capacitor, so that's supposed to be the capacitor current, not the switch current. We talked about the switch voltage, but not the switch current. So the diode and the capacitor current. So the diode current when the switch is open is given by that, which is basically equal to the current flowing through the primary winding with the turns ratio, because we are dealing with a transformer. And we use the KCL at the node to find the current which will be flowing through our capacitor. Therefore, this expression we have over here gives us the current which will be flowing through the capacitor when the switch is open. The switch voltage. So when the switch is open, there's going to be a voltage across the switch, and we want to make sure that our switch will be able to handle that voltage. To do that, we did a KVL and show that the switch voltage is going to be Vs minus V1, where V1 is the voltage across the primary side. That is the magnetizing inductance when the switch is open, and that voltage is given by that VO multiplied by the turns ratio N1 over N2. So we show that. Now we need to find the average. So all along when we've been dealing with the DC-DC converters, you know that we need to find the change in the inductor currents. We also need to find the average, and then from the average we can find the minimum and the maximum. So we have looked at the change in ILM for both when the switch is open and closed. We've looked at some of the currents through the diode and the capacitor, and also the voltage across the switch, because it's a very peculiar case where we need to make sure the diode can withstand its voltage when it's reverse biased, and the switch can also withstand its voltage when it is open. Now we are moving to the point where we need to find ILM. You can call it average. So we need to find the average current of the inductor, and knowing that average value, so this average value is going to be there, knowing that in addition to the change in inductor current for the magnetizing inductance, which we've calculated already, is then going to help us to find the maximum current and also to find the minimum current, to make sure that this minimum current is always greater than 0, to make sure we are operating in the continuous current mode for the power supply. So that is going to be our next target, to find the average, and then we've used that one in addition to the change in inductor current to find the minimum and the maximum current. So how do we find the average? Same thing, power supplied by the source should be equal to power absorbed by the load. So this is the relationship we've been using all along for all the DC-DC converters to find the average current which is flowing through the inductor. If you make these substitutions over here, where Is is equal to the average current flowing through the magnetizing inductor multiplied by D, because the Is is the same as the current which is flowing through the magnetizing inductance when the switch is closed. And then when the switch is open, there is no current flowing through Is. So Is average is given by that expression, which means when you make the change of subject, this is what we have. And when you do the substitution, you come out with an average current which is going to be flowing through the magnetizing inductance. So this gives us the expression for the average current which will be flowing through our magnetizing inductance. you can substitute, because we already know the relationship between the output voltage and the input voltage for the flyback, so we can make a couple of substitution over here. But this is a basic relationship. That is a basic relationship, and if we go ahead and make the make a substitution, then we can reduce this expression to what we have over here. But that's just dependent on you. You have the basic relationship which you can use to find the average current which will be flowing through the magnetizing inductance. Knowing that, we can then find the maximum and the minimum like I explained before. So the maximum is going to be what? The average plus change in the inductor current divided by 2, and then the minimum is going to be the average minus change in inductor current divided by 2. These expressions, we already have them, so it's just a matter of substitution. The main focus is how do you calculate the maximum, and this is the same for all the converters we've looked at, and how do you calculate the minimum. And this expression, this general expression, is the same for all the converters we've looked at. The only difference is the actual formula which defines what the average is and which defines what the change in the inductor current is going to be for that particular specific converter when you are dealing with it. Very good. So knowing, let's go ahead and erase some of this. Knowing the minimum inductor current which is going to be flowing through the magnetizing inductance, we can then use that expression, which is the expression over here, to find out what will be the minimum Lm, everything has been constant, to make sure that we are going to have continuous current of operation right over here. So we want to make sure our ILM minimum is going to be greater than 0. When you do that, then the minimum LM which is needed, everything has been constant, is given by that. So this is where all the critical values come in, and you can use that inequality ILM, this inequality greater than 0, to find all the other critical values. For LM minimum, that is the expression we have for that, for the flyback converter. Like we said before, the flyback converter is very similar to the back boost. Therefore, when we come to the output voltage ripple, the two are going to be the same. So the expression we use to find the output voltage ripple for the back boost is going to be the same as the expression we are going to be using to find the output voltage when it comes to the flyback converter. The equivalent series resistance. So we normally calculate the ripple due to the equivalent series resistance, and we know the expression we always use to calculate that voltage, change in voltage due to the ESR is always changing what? The capacitor current multiplied by the RC, which is equivalent series resistance. In the back boost, we know that this change in inductor current is equal to what? The maximum inductor current. In the flyback is the same, but then we have to take care of the transformer, the turns ratio. So you have to take care of that. So it's still the maximum. So the change in IC is still the maximum current, inductor current flowing through, this time the magnetizing inductance multiplied by the turns ratio. We have to make sure we are taking the transformer into account. So very similar expression. The only addition in this scenario for the flyback is we are taking the turns ratio N1 over N2 of the transformer into account when we are calculating the change in the voltage which is due to the ESR. And the last thing I want to talk about is the various waveforms of the flyback. So I brought quickly the flyback converter over here. So the magnetizing inductance, that's basically what we've been using to derive all the expression for this analysis, and we expect the current to be greater than 0, to be continuous, switch on and switch off, to make sure we are operating in the continuous current mode. Our source current is positive when the switch is closed and is 0 when the switch is open. So it's the same as equal to ILM when the switch is closed. Our ID is 0 when the switch is closed because it becomes reverse bias, but then it takes on the same value as what ILM in addition to the turns ratio. So don't forget in all this, especially for the diode current, we have to make sure we are taking care of the turns ratio. That's very, very important. IC we saw before, when the switch is closed, is going to be constant because it's going to be the load current which is going to be discharging through that. But then when the switch is open, right, we have the expression for IC earlier on. So when the switch is open, we derive the expression for IC, which is going to take on this particular form. And the last one I want to show here is the voltage across our magnetizing inductance. So when the switch is closed, we know it's very clearly equal to what? Vs. When the switch is closed, very clearly is equal to Vs. But then when the switch is open, we have to use the voltage which is established on the secondary side, which is the output voltage, to find that. And how do you find that? Knowing that one, which is going to be equal to what? The negative of V2, then we can use the turns ratio to work that one back to obtain the voltage across our magnetizing inductance when the switch is open. This is going to end our session on the flyback converter analysis. Thank you very much, and hope to see you in the next session, which is going to be on the forward converter.